if we look at timing analysis, actually an embedded system is often more interesting than a smart card. With a smart card, you're bound to the official interface, and if in the official interface there's no timing variance, then that's almost all you can do. In an embedded system, you have a lot of peripherals on the board that all happen and signal things at a certain time. And you only need to have a few that actually correlate to the timing that you're interested in to get a real attack. So other things are runtime issues with CPUs, with cache timing. If you Google cache timing attacks, you'll see quite a few things. And that all applies to software systems in embedded systems too. One thing that with timing that you can do with power measurements and EM measurements is increase the accuracy. Like I said, if you have a smart card and you can just see input and output, if I measure the power signal of that same chip when it's happening, I might see timing variation in the power signal. And then still it's a timing attack, but I use the power signal to do it. A very well-known timing attack is actually this, that if you do something in software, and especially if you don't really control or understand the API, you may have a problem. And one that occurred, I think now 2 years or 3 years ago, is a timing attack on the Xbox. So what you see here is an Xbox with a small helper board called an Infectus board, which is an FPGA. And it's used to carry out a timing attack on the signature checking of the bootloader. So the way it worked is that the Xbox is protected by a secure boot chain, and it calculates HMAC, SHA-1. An HMAC is a hash of the whole firmware with a secret key. And in the end, you get 16 bytes that say, okay, this is a real one. And you need to compare it to the one that you stored. And this is where the software comes in. The software naive implementation did a byte-by-byte comparison and stopped if there was a first wrong byte. So you get a timing dependency. That if there are 5 bytes wrong is a different time than if there are 10 bytes wrong. And this timing could be measured in a very specific way. What they did is they put the Infectus board on the system. It could modify the NAND flash real time, and then it would observe a diagnostic port. So these were 8 bits. They were exported off the chip. They were just on the PCB. You soldered the wires to it, and it would give an error code every time the hash was wrong. And by just timing how much time there is between the reset on the CPU and when that code appeared on the bus, they could time the difference in the comparison. And then it just, the small board just brute forces that with help of a PC, and it takes about 2 hours to find 16 bytes. And that's the way the Xbox was broken, and they could run Linux on it. So this is to show that these are actually real attacks. The thing is that this only occurs after the Xbox chips have been protected to such a level that you don't get any easier access in another way. And it's fixed, of course. Power analysis. So what you see here is a board of a BlackBerry. And the idea is, okay, this is a CPU. It has a secret key. How do I do a power measurement on this CPU? And if you look really carefully, you don't even see traces on that PCB. It's just one flat layer on top, because all the layers are used in the middle of the board. So to be able to actually access the power line, you either have to go all the way off the board and just measure the external power, but then you're measuring power for everything on the chip, which is really noisy. Or you have to make some kind of interception somewhere in the middle of this PCB design, which is quite a challenge even for an electrical engineer with some soldering skills in BGAs, etc. So a power attack might seem attractive. There are no countermeasures, but it still can be quite a bit of work. And sorry? No, because that's not a power measurement. What you measure then is just the input voltage.
Yes, but you have current flowing from one side to another side. So we have a resistance in the PCB, and we measure the differential voltage between two capacitors.
Well, that's often not the way it's implemented. If you look at the design of how, so the idea is if there are a lot of decoupling capacitors often on the board, that you can use them to do your measurement. Actually, the point is that most of the time you want to get rid of all the capacitors because they flatten out your power profile. So it's more the opposite. You want to find one place to cut the wire, do your power measurement, or inject your own power, and remove all the decaps that are present to get as much spikes in the power signal as you can get, because the spikes are the ones carrying the information. The last point, basically you always need considerably more knowledge on the target compared to a smart card. EM analysis. First, maybe an explanation of what electromagnetic analysis is. Here in the next slide, I have a picture of a probe tip, and that's the probe that's mounted here. And in the tip, you see a very, very tiny coil. In the probe itself, the metal housing is an amplifier. So what it does is it picks up the local EM field around that coil. And that's a technique you can use to have kind of non-invasive measurements. So we don't have to open the PCB. We just float this thing above the chip. And I'll show you in a minute a little bit of how that works. What it does, it adds something called the dimension of space. Instead of a power line, which is one dimension, you now have an XY where you can put your probe and you will measure different things at different places. This is especially interesting, again, from a smart card perspective, where you have countermeasures on the power line. They have a lot of capacitors and you try to flatten it. But you don't have control in your design, or not much control in your IC design, on how the field will look like above the chip. So this is what that tries to exploit, is to figure out if EM can then be better. The big question is, of course, where do you need to be with your probe? And there's no clear rule yet to know where the place is. So I'll try to show you a little bit what comes out of that if you put it above a board here. What we see is that EM generally tends to add if it's a small area you're interested in on a relatively big chip, a big die. So if it's a microcontroller, then most of the time the power contains all the information and is a better signal. And of course, if it's non-invasive. So maybe time for a quick demo. So what have I got here? I understand it's a bit far away, so I have kind of zoomed in. Actually, what you have is an XY, motorized XY stage. It can move. Beneath it is a small board with a processor, and it will be running an RSA. It's a very simple implementation of RSA, also not a very long key size, but it's just for the principle to show you that you actually do see different signals when you do these measurements above a chip. So for that, I have to switch. Oops, this does not look good. I need to plug this in. It's always with demos, of course. That sounds good. Okay, the whole screen looks a bit warped, but that's because of the sizing. So what we can do here is we can, and this is part of the software that we have to do this analysis. So there's commercial solutions. There's also open source software on the internet to do such an analysis. What I can do here is I can operate the motorized stage. I need to select the correct COM port. It's using a serial cable to the development board, to the CPU, to feed it with data for the RSA. I also have a short video. You'll see that there's also a trigger line, which is on an LED. So we're using a GPIO line to trigger at the time of the RSA. And with this, I set the positions. Oh, wrong way. So now you probably don't hear anything, so I can try and play the movie at the same time. Let's see if this works. Okay, this doesn't work.